welcome to my channel. This is the first video on a series of videos about math, and we're starting from the very bottom. This is where I started. This is where everybody needs to build their foundation. I'm still on my math journey. I'm talking about pre-algebra, baby. I'm still on pre-algebra, but I've dived in pretty deep with the subject. I'll be talking about arithmetic, which is before pre-algebra. So stay tuned. Don't leave just yet. Okay. What do we got here? Numbers, right? They're called natural numbers, or you got your counting numbers, or they're called counting numbers. When we refer to them as, when we give them these names, they're included in a set, and there's different sets. Okay, I'm not diving into that right now, but yeah. Okay, so when we get deeper into math, you come across the term constant. 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 That looks like a no. Constant. Okay. Now, what does that mean? Well, have you actually really thought about it? Already, you have a variable which is created in contrast to constant, but constant stays the same. Now, how do I draw sameness? Like, how do I draw that? I don't know. But pretend I drew it. Okay, so, but yeah, it's a constant. It stays the same. It doesn't have any kind of meaning towards it. Right? Like, if there's no movement to it, can you say it exists? Okay. But yeah. Okay, then now we have a variable. So, opposite of constant, something that changes. So it changes value. It could be any value, actually. Any value. Any value. And it's actually quite hard to write at a straight level here and still talk to the camera, but it has any value, and it's also treated as a whole. It's actually treated like a constant. But yeah, these are the two forms which you may have as a, let's see, a makeup, I guess, or a property of a expression. What's interesting about constants is, so I mentioned that they don't have any kind of movement. It's not until we add a plus sign, a minus sign, a division sign, or a multiplication sign do they actually have movement. Now we have an influential factor here. Which brings meaning to these objects here. Now, so we have three characteristics of an expression. This is what we call an expression. Okay. We have three parts. So we have our I don't know, we can call them our construct. I like to use the word construct a lot. But think of it as the rules and constraints, the rules and constraints in the construct. This is a gear, if you guys didn't know. And the gear is like a machine. Um, so you have your constraints and your rules uh, in, I guess, in the background of the machine. So it's like the engine without the gas. You know what I mean? Like the engine. You have your engine block. You have all the objects and everything. Like it works. It it has its purpose, but without the influential life energy put into it. Without that, you might as well say it's useless. So it's good as a paperweight. But yeah, so so basically these symbols right here are the energy which give meaning and value to us, um, to the machine. But yeah. Okay. Now I'm gonna explain a few principles that I came up with here while studying math. It's written in my journal, but um, yeah. So I find it interesting that all these numbers, every number that we can think of, is made up of just 0 through 10. That's interesting to me. But here we have the introduction of place values. This is our ones place, our tens place, and our hundreds place. Uh, and what this is made up of. If we were to break this down, it's called our hundreds place because we have 9 100s, which is 900. And this is very important to understand uh, very deeply, because then you can really start messing with like increments, maybe like decimals or fractions, that you have an easier time. And you also have an easier time doing your arithmetic. But okay, so our eight, this is our tens place. So we have 8 tens and then 5 1s. And okay, what I have here is it's a principle that I see everywhere in mathematics, and it is like a growth and then like a reduction all the time. Everything is like everything larger, everything larger is just has an equal smaller like representation. Blah, blah, blah. Okay. Okay. So yeah. So you start from 0, and then you have 5 counting places. But then once you get here, you get like you have 8 times 10, and then to get to the next place over to your hundreds, you got 10 times 10. So everything in the places, in the place values, in the places, they are growth by 10. So 10, 10, 10, 10. Okay? But yeah, so this is really important to understand. Everything in mathematics, the smaller equals the larger, and the larger equals the smaller equals the larger, and the larger equals the smaller. Everything is a different representation of the same thing. Like the same value has many expressions, right? So take 40 for instance. We can say this is at its whole or like its peak or something, but we usually think of 40 as a whole, like we treat it as a whole, and we do our factoring or our arithmetic with the whole. But like you'll just do 40 plus 40, that's 80, but you never do like 2 times 5 times 2 times 2 and then you don't break down the whole to its finer, smaller parts and then multiply it all out to get the same answer that you would if you were to do 40 times 40. But yeah, so this is called factorization. Um, but it's got this principle here that I really want to show you guys and like ingrain it in your skull. I want to like tattoo it right here on your skull. But everything is this factorization of primes is the same as this. Different expressions of the same value, the same meaning. But this is more broken down at a lower form, and it can grow or reduce into its whole form or its peak. You call it its peak or whatever. You'll see this principle also at work with addition and subtraction. Adding, you're growing. You're subtracting, you're taking away. Uh, uh, and then your multiplication and division, which are just different forms of addition and subtraction. Multiplication is like you have your, like say you have just 2 4s, an array of 4. You have 4 and 4. But you have 2 lines or rows of 4, so you can just say times 2, basically addition, and you get the same answer, which is 8. But yeah, this also is another principle here. So we have our whole, the 72, but then you have different paths, to the same answer. So, but also this can equal every single factorization that leads up to this. This is the path. This is the end goal, or the peak, and they can be interchanged, and they all mean the same thing. 72 means that. 72 means it's primes of 3 and 3 and 2 and 2 and 2. Yeah. And that and that. Okay. Now, ain't that interesting? This whole principle of growth and refining. You could say growth and reduction. You could also say the word metamorphosis. Number is a metamorphosis of another. The symbol, the expression of it is all interesting stuff. But one more principle I want to share: larger to smaller. You hit the 0 point, and now you get back to larger. This is this whole principle of refinement, of growth, just addition, multiplication, subtraction, division. Here we'll have all our 0, and then we get our 1s all the way up to 2, 3, all the way to infinite. And then now you could go even smaller to your 0.1, 0.01, 0.001, all the way into infinite. This is also a reductions in tens place. So this is, once you get past 10, everything is just growth by 10. This is also just a reduction by 10 as well. The tens place. This is our tenths, hundredths, thousandths place. I guess the biggest thing to share here is scale. Scale is everything in math. The better you understand scale, the better time you're going to have in math. Now, numbers, they go down like this. I can't explain yet why, but they do. Or you could think of it like like a flash. You got this, and then it computes, and then it flashes away, and then it has its smaller number. What is that? That's 72, right? Yeah. It like grows. It's layered. Like this this method here even applies to this even applies to polynomials, expressions like algebra. Like you have this. What is this? X plus 3, x minus 3. it's just like, there you go again. It's just this represents, this is a larger representation, or it's a different representation of its smaller parts. So this, basically, you could look at this as your whole, and then these are your prime factors, your prime numbers. So now you have arithmetic principles colliding into uh, algebraic expressions, algebraic notation, I guess we'll call it, or problem.